Hello everyone and welcome to the Inorganic TUTOR'S Institute. My name is Nasiruddin Gate and I will be your tutor for actuarial science and statistics courses. So a little bit of an intro. I am a graduate of the University of Cape Coast where I studied actuarial science, and I had the honor to graduate as valedictorian of UCC class of 2025. On this channel, my goal is very simple: to teach actuarial and statistical concepts in a manner that will prepare you for your examination and real-world problem solving. From time to time, I will be teaching using my screen, but I would want this to feel as close as possible to an in-person interactive class. So in today's lecture, we would start with introduction to probability, which forms the basis of risk theory, actuarial science, and most statistics courses, especially those related to mathematical statistics. So let's kickstart and see what we have for the day. So our learning objectives for the day are as follows. So at the end of this lecture, you should be able to 1. Define a random experiment, 2. Define a sample space and events, distinguish between simple and compound events, apply the classical definition of probability, and solve basic probability problems. So now let's proceed to the main agenda for the day. We'll start with what we mean by a random experiment. But before that, I would like to explain to you what we mean by experiment here. So when we say experiment in, say, probability, we are not generally talking about the ones we go to the lab and to mix chemicals and make some reactions and stuff. No. When we come to probability, experiment here means that any activity that results in one or more outcomes. So if you perform any activity and that activity has the potential of producing an outcome or a result, then we say that activity is an experiment. So let's say a football match can produce 3 different outcomes. There might be a win for one team, a lose, or a draw. So because there are 3 outcomes to the game, we say this activity is an experiment. Or a student taking a test. He or she has the potential of scoring 3/20, 6/20, 19/20. So these are all possible outcomes or possible scores that the students can get on a test. In that case, we say the activity is an experiment since it produces different outcome, or there's a possibility of different outcome. Well, the outcome could be just one and it can still be considered an experiment. So when there's an outcome 1 or more, we say we have an experiment. Now let's come to random experiments. We say it's a process that has a well-defined set of possible outcomes. So we are saying for the experiment to be called a random experiment, firstly, the outcomes that might be realized after the activity is conducted should be well known even before the activity starts. So we should be able to tell that this activity that we are going to conduct is either it will lead to this or to this or to this and nothing else. Okay, we should know all the outcomes that have chances of occurring. Okay, so if you're not able to tell us all the outcomes that we might see after conducting the activity, then we cannot conclude that the experiment is random. So you should be able to list all the outcomes even before we conduct the experiment. This is what would fulfill the condition of being a random experiment. So after having knowledge about the possible outcomes, the second condition is that it should have an outcome that cannot be predicted with certainty. Okay, so we know that the experiment or the activity can lead to this, can lead to this, can lead to this, but we shouldn't be able to tell with 100% accuracy that, oh, when you do this, it will definitely lead to this. When Real Madrid plays with Chelsea, it will definitely be a win for Real Madrid. If that is the case, then we cannot say it's a random experiment, because in this case, you've predicted with 100% accuracy. But remember, there are chances that the team that we predict to win might lose. That makes the activity completely random. You can't tell with 100% accuracy that this is what will happen after the activity. That's what makes it a random experiment. So whenever you hear a random experiment, think of two things. One, can I list the set of possible outcomes? Do I know whatever will happen or might happen when I do this? And two, can I accurately tell the outcome, or I need to perform the activity before I can see what the outcome is? So once these two are satisfied, we have a random experiment. So we have some example, or say, okay, one example to test our understanding. So the example we have here is predicting the weather for a day. So first, we should be able to tell what the outcomes will be. It could be sunny, cloudy, rainy, windy, or whatever. We should be able to list all what we are expecting tomorrow. You should be able to list them. And aside that, you shouldn't be able to tell with 100% accuracy that it's going to rain tomorrow, or there's going to be no rain tomorrow. You shouldn't be able to tell with 100% accuracy. And that's the case. That's why we can classify predicting the weather for a day as a random experiment, because the outcomes are known and we can't tell with 100% accuracy or certainty that this particular outcome is going to show up tomorrow. We can only give probabilities, but we can't predict with certainty. So I have this test your understanding here. For most of my slides, I will be having this section so that we just test how well you understood what I explained. So the problem here is, as a student score on an exam a random experiment? So you can pause and think about this. Okay, so a student score would definitely be a random experiment. Why? Because first, we know the outcomes of the test that, or the exam that the student is going to take. So if the exam is out of 60, then the possible outcomes are 0 or 1 or a 2, 3, 4 or 60 over 60. Okay, those are the set of possible outcomes after taking an exam. And the second condition is satisfied because we cannot tell that when the student takes this exam, he or she is going to get 35 over 60. We can only assign probabilities, but we can't say that once you take this exam, you will get 42 out of 60. We can't do that unless the exam has been taken and we realize the results. So this qualifies to be a random experiment. So that's it for random experiments, and we move on to the next session of the lecture. So what we have here is the sample space, and arguably one of the most important terms in probability, no doubt. It is the sample space. So when we say sample space as defined in the slide, is a set of all possible outcomes of a random experiment. Okay, so when you have an experiment, all the outcomes that have been listed so far, so say sandy, cloudy, windy, rainy, these are the outcomes. Okay, and a set that contains all these outcomes is what we call a sample space. So if you are going to take a test out of 60, the possible outcomes are 0 over 60, 1 over 60, 2 over 60, up to 60 over 60. So this set from 0 to 60 is what we call a sample space. If you are rolling a die, what are the possible outcomes? You might get 1, 2, 3, 4, 5, or 6. So the sample space S is equal to, open bracket, 1, 2, 3, 4, 5, 6, close brackets. It's a set of only the possible outcomes. So you can't include 7 in this set. You can't include -5 in this set. Why? Because they are not possible outcomes of rolling a die. So we have these two important properties that we have to take note of. So we have mutually exclusive outcomes. Mutually exclusive is a very important term in statistics, or precisely probability. When we say an activity or an outcome is mutually exclusive, or let me say two outcomes are mutually exclusive, it means that the two outcomes under consideration cannot happen at the same time. Okay, so when you have rolling of a die and the set or the sample space is 1, 2, 3, 4, 5, 6, we are saying that 1 and 2 are mutually exclusive, because if you roll a die and you get 1, there's no way 2 will also show. It's not possible. If you roll a die and you get 3, there's no way 5 will show. So when one occurs, the other one does not. That's what we term as mutually exclusive outcomes. So all the outcomes in the sample space, they can't happen at the same time. We need just one to represent the outcome of the experiment. 2 elements cannot show up as outcome of the experiment. So if the sample space is rainy, sunny, cloudy, windy, we need just one outcome to represent the weather for tomorrow, not 2. So that's what we term as mutually exclusive. 2 of them, or 2 of the outcomes, or 2 or more outcomes cannot occur at the same time. The second property we have here is exhaustive outcomes. When we say exhaustive outcome, is also a term that moves closely with mutually exclusive. So exhaustive means that the outcomes that you list, there shouldn't be a case that there is another outcome and you don't include it. Okay, So if you are listing the sample space for rolling a die, you can't list 1, 2, 3, 4, 5 and leave 6 out. In that case, we say your sample space is not exhaustive because there is an outcome that you have taken out, which doesn't make your sample space complete. So for it to be exhaustive, it should be in such a way that you list all the outcomes that are possible. You don't leave any of them out. So these are the two most important properties of a sample space. One, the elements that you list, two of them shouldn't happen at the same time. Only one should happen after we complete the experiment. And two, the outcomes that you should list, you shouldn't take any one that is possible out. So in a case where an outcome is possible, then you just take it out or you don't include it in the sample space. That makes your sample space totally wrong. So in this test, you understand, we have list the sample space when a die is rolled, and I've mentioned this severally. So the set of possible outcomes when you roll a die is either a 1, 2, 3, 4, 5, or 6. Let me demonstrate to you how to write the set of a sample space. So we write S is equal to, then you open the brackets, just a small curly brackets. Pardon me for my writing. Let me come again. So we have S equals, open brackets, 1, 2, 3, 4, 5, and 6. Then you close the brackets. Yes. So this is how we write sample space for rolling a die. And this is what they expect from you in an exam. So S is a set equal to 1, 2, 3, 4, 5, 6. Don't leave any outcome out, and make sure when one occurs, any other outcome cannot occur. So we move on to the next section of our lecture. Okay, so we proceed. So we have an example here about the sample space when two die are being rolled. So at the same time or simultaneously, or so similar terms to this are a single die is rolled twice, or two fair dice are rolled simultaneously, or two fair dice are rolled at the same time. These are all similar terms that mean the same thing. So there is a set of possible outcomes. So you can represent that using a 6x6 table where you have the outcomes for the first die on the first, let me say, okay, so we are presenting an example here about the sample space. So we have two dice which are being rolled. And other similar terms or statements you can see are a fair die is rolled twice, or two fair dice are rolled simultaneously or are rolled at the same time. This means we roll a die, and we look at the outcome and we write it down. Then we roll the die again and look at the outcome and write it down. So we now have two pair of outcomes. Or we roll two die, we check the outcome on the first die, we write it down. We check the outcome on the second die, we write it down. Okay. So when you do that, we say these are the set of possible outcomes. So we list the outcomes for the die 1 vertically, then we list the outcome for the die 2 horizontally, then we create a 6x6 table. So this is how the table is being created. Let me turn on my one, and we determine 1 by matching the outcome of the first die with the outcome of the second die, all being 1. So you get 1 on the first die, you roll again, you get 1. That's what we have as 1 here. Then we go to 1 2. 1 2 means we roll in the first one, we obtain a 1. We roll in the second one, we obtain a 2. 1 3 here means we roll the first one, we get 1. We roll the second time, we get a 3. So that's how we fill the first row of the table. Then we go to the second one. 2 1 means that we roll, and on the first row we get a 2. Then we roll on the second row, we get a 1. So this is just some game you can use to entertain yourself when you're bored. Not really a big deal. So when you come to this particular row, we have 5 1. 5 1 means that the first die produced a 5 and the second die produced what? 1. 5 2 means the first die produced 5, and when we check the second die, or when we rolled it the second time, we had a 2. So that's what this table is speaking of, and it's a sample space for 2 dice. So it's saying when you roll 2 dice, what are the possible outcomes? The outcomes could be 3 2, meaning the first one will produce 3, second one will produce 2. The outcome could be 4 5, meaning the first one produces 4 and the second one produces 5. So that's how simple this table is, and that's the interpretation to every single point you see in the table. They are just outcomes from the first row and the second row being combined. Okay, sure. So we proceed to the next part of the lecture. So from the previous slide, the number of sample space is 36. We can do that counting. So we have, we can use this basic mathematics about area, length times the width, right? So we have 1 2 3 4 5 6 on the width, then 1 2 3 4 5 6 on the length. So 6 by 6 gives us 36. Well, if that's a problem, you can count them individually from the table, and that's not really a problem. Okay, so that's how to get a sample space for 2 dice. So if the dice are 3, then we have 6 times 6 times 6. Okay, sure. So as some examples, find the probability that the sum is 7. Find the probability that the sum is even. Which test your understanding. Which outcomes correspond to the sum being 9? Count them. I would want us to proceed and revisit this example or this particular slide after talking about events. Yes, this example will be best solved after understanding what we mean by events in probability. So let's go to the next slide and see what we have there. Then come back to this later on. Okay, so an event is any subset of the sample space. Remember, sample space lists all the possible outcomes. Okay, but an event takes off some parts of the sample space, or you can even consider everything, but that's in rare cases where the event will be the same as the sample space. It's usually a subversion of the sample space. So the sample space will list all the outcomes, but the event will list some or even none of the possible outcomes. Okay, so we have two types: a simple event and a compound event. So when the event lists just one outcome, we call it a simple event. So let me turn on my, so if we have event equals 1, if you have event equals 1, it means that when we roll the die, we are interested in 1 showing up. When we roll the die, the event we are only interested in is that you get a 1. Aside 1, the rest are not what you are really interested in. So you don't succeed when you roll anything aside 1. Another event can be 6. There's also a simple event because it has just one outcome. We are only interested in getting 6. If you don't get 6, whatever you get is outside what we are interested in. Okay. So what then would a compound event be? The compound event comes in when the outcome is now more than 1. Let's say we are interested in an odd number showing up. Okay, an odd number showing up. Then the event of odd numbers will be either 1, 5. Sorry about that. I hope you can see my 135. Yeah, let's manage it like that for now. Sure. So I was saying, for the compound event, it's not just one outcome that will accomplish the goal. No. If you want odd numbers, then you shouldn't just target only 1, because if you get 3, that's also an odd number, and the event has been satisfied or fulfilled. If you get 5, good, mission accomplished. You said you want an odd number. So if I produce 3 or 1 or 5, it still falls in the event. Okay, so that is what differentiates a simple one from a compound one. A simple just has only one outcome. You just have to do just one thing to satisfy the goal. But for compound events, we give you multiple choices or ways you can accomplish the mission. So if you get 1 or 3 or 5, you still fulfill the goal of getting an odd number after rolling a die. So let's visit the previous example and now discuss how to find those probabilities. Okay, so example 1, Find the probability that the sum is 7. Find the probability that the sum is 7. So the first thing we have to do is to list the event of sum of 7. When will we say that yes, we've accomplished the goal of getting a sum of 7? Imagine you go to a casino or anywhere, and the rule is that if you roll 2 die and you get a sum of 7, you maybe win some prize or anything. Do you think it's only one pair that can get you a sum of 7? Do you think it's only rolling 1 on the first die and 6 on the second die that will give you a 7? No. There are lots of ways to get a sum of 7, not just one. So in this case, sum of 7 becomes a compound event because the event contains more than one outcome. It's not only one outcome that will give us 7. So let's look at these outcomes and proceed. So we are using the sample space from the previous slide. This sample space is what we are using. And remember, an event is a subset of a sample space. So from this sample space you see here, we will pick the elements or the points that gives us a sum of 7. You can even do that on this slide. So event of 7, so let's write it as E7. Event of 7 can be obtained from, so taking the first row, 1 6 gives us sum of 7. So this is what we do, 1 6. Okay, then taking the second row, that's it for the first row. None of them will give you a sum of 7 again. Now checking the second row, 2 1 doesn't give us 2 2, 2 3, 2 4, 2 5 gives us sum of 7, 2 5. Then on the third row, 3 4 gives us sum of 7. On the fourth row, 4 3 gives us sum of 7. On the fifth row, 5 2 gives us sum of 7. And on the sixth row, 6 1 gives us a sum of 7. So this is how to obtain sum of 7 from the sample space. So you can see this is a subset. It doesn't contain all the elements of the sample space. It contains some. But you should make sure that whatever is in the event can be found in the sample space. You can't go and write 7 0 as event of 7. Although the sum is 7, but remember 7 0 is not in the sample space because none of the die contains a 7 or even a 0. So you should make sure the event that you list is in or can be found in the sample space. So this is the event of 7, and it's a compound event because it has more than one outcome. Okay, so now how do we determine the probability? So we determine this probability by knowing the number of outcomes in the sum of 7. So how many possibilities gives us so 1 6 is 1, 2 5 is 2, 3, 4 is 3, 4, 3 is 4, 5, 2 is 5, and the last outcome is 6, 1. So 6 outcomes gives us a sum of 7. 6 outcomes give us a sum of 7. So you divide this by the total sample space. Well, we will discuss this further in the future slides, but let's start some intro on that. So you divide the number of outcomes that will give you 7 by the total in the sample space. Okay, so if you have 36 options and you are interested in, let me say, 6 particular ones in the 36, so the chances of picking those ones are 6 out of 36 if you are selecting at random. So you are picking at random. What is the chance that you pick any of these 6 that we have marked? Okay, so you have 6 balls and we've marked we have 36 balls and you've marked 6 of them. So the chances of picking any of these 6 at random is the 6 out of the many 36 that we have. That will give us the probability of selecting any one of the marked balls. So in this case, to get a probability of sum of 7, we divide the outcomes that will give us sum of 7 by the total sample space. I guess you can then do the example 2 yourself. So a little guide. Write events of even number. As a set, and list all the outcomes that are even. So if you check the previous slide, 1, 1 will give us the sum being even. 1, 2 will be odd. 1, 3 will be even. 1, 5 will be even. 2, 2 will be even. So you list all of these outcomes. So after listing them, cross-check your events whether each of the elements you've written there, when you sum them, you get an even number. Okay, so when you do that and you think everything is complete, you've selected all the outcomes that gives us a sum of 7. When you are through with that, count them and determine the number of the events of even. How many outcomes will give us a sum to be even? If there are 16, you write them down. If there are 15, you write it down. So when you count the number in your set and you get, say, 16, then the probability of getting the sum to be even will be the 16 over 36. As simple as that. So whenever you are given or asked to determine the probability, you first list the sample space, then look at the events that will satisfy your goal. So if they want the sum to be 8, look at the elements in the sample space that will satisfy the goal of being a sum of 8. So you check the elements one after the other. Okay, this one, when I sum them, will I get 8? 2, 4, it won't give me 8. 3, 5, okay, 3, 5 will give me 8. Then you go and list it as part of the event. Okay, this is 4, 4. Okay, 4, 4 will give me, then you list them down. So after you list them down and you are true or certain that you've listed all the outcome that will give you sum of 8, now you count them. How many elements do I have in the event? Okay, I have this 4, I have this 5, I have this 6. Then you divide this number of elements you have by the main sample space. That will give you the probability that the sum is 8. Okay. So that's how to move about with it. Don't worry, we will have sessions where we will solve multiple questions. It will just be purely for solving questions and nothing else. Well, nonetheless, make sure you also understand these examples I present here. So let's proceed from where we left off. So we discussed this. We are now here. Okay, so we've been given a 9 scenario and we have to list certain Okay, so let's look at this scenario and use it to answer the questions below. So the scenario is a bag contains 2 red, 3 green and 1 blue marble. So there's a bag that contains different marbles of different colors. So 2 are red, 3 are green and 1 is blue. So one marble is then drawn at random from the bag. So you randomly pick any marble from the bag without looking at it. Okay, so that's a random experiment. Now the question is, define the sample space. Remember, sample space is a set of possible outcomes. So what could be the results when we draw one of the marbles at random? So what can we possibly get? Okay, so I would list them, but you should take note that we will treat each ball separately. That is what I mean. If you write sample space and you write red, you need to specify which of the red balls. So we have red 1 to denote the first red ball. Then R2 to denote the second, sorry if I said ball, marble, the second marble. Then G1 to represent the first green marble, G2 second green marble, G3 the third green marble, and B to represent the blue marble. Okay, so that's what I mean. You treat each marble distinctively. So you don't combine them and just use R to denote the two of them. No, you treat each of them separately. So whenever you have a problem like this, just know that the sample space contains distinct elements. So although there are 5 red marbles or 3 red marbles, you don't write red to represent all the red marbles. No, you write R1, R2, R3. Okay, good. So this is the sample space. The sample space is a set R1, R2, J1, J2, J3, and B. Okay, sure. So the second question here is, identify a simple event. So let's look at an event which has just one possible outcome. So we can find the probability of selecting, let's say, a blue ball. Okay, find the probability of selecting a blue ball. In this case, that event will be equal to only B Okay, that event will be equal to only B, because it is only selecting a blue marble that we can get a simple event. If you say selecting a red marble, you will end up getting a compound event. Okay, because red has two outcomes, and each of the two marbles satisfies the condition of selecting a red marble. So for red and green, they can't give us a simple event because they have more than one element. Okay. So identify, the third one says identify a compound event. So that's what you've been given the hint there. So when you select a green ball or a red, when you select a red marble or a green marble, it results in a compound event because they have more than one outcome. So selecting a red marble, for instance, will be equal to either the first one or the second one. Okay, so this is a compound event. If you want to make it a simple event, you say, and the event of selecting the first red ball, okay, that one reduces it to a simple event because you specify that you want the first red ball and not the second. So if you generalize it, event of selecting a red marble, it's R1, R2. But if you say the first red marble, then we have R1. Pardon me if I'm confusing the ball with the marble, but it's the same thing. I mean, the same item. Yes, it shouldn't really cause some confusion in this discussion. Okay, sure. So let me take it again. So a bar contains 2 red, 3 green, and 1 blue marble. So we have to define a sample space. So the sample space is each of the marbles in there. They are all capable of being selected. So the sample space is R1, R2, J1, J2, J3, and B. Now the second one says identify a simple event. So if an event that has just one outcome. For instance, selecting a blue marble has just one outcome. Or selecting the first red marble has just one outcome. Identify a compound event. So selecting a red marble without specifying which of them is a compound event, because when I choose the first one or I choose the second one, I satisfy the condition or the goal. Okay, so just selecting a red marble becomes a compound event because it has more than one marble. Now, additional practice for you: create your own scenario with dice, coins, or cards and state simple and compound events. Okay, so we had some discussion about the die, so you can do more practice by creating a scenario for yourself. Okay, so let's move on to the next slide, where we have classical probability. So classical probability is what we've been discussing so far. Examples about dice, example about picking marbles, example about rolling a die, tossing a coin. They are all under classical probability. Why? Because we assume each outcome is equally likely to occur. When you are tossing a coin, you know the chances of getting a head is the same as chances of getting a tail. Okay, yes, we say it's 50-50. If not so, we will have a particular side of the coin that we will always choose. But because the chances are almost the same, we don't really think much when we are told to select a side of a coin, because we know that each of them can equally occur. It's just by chance. Similarly with a die, when you roll a die, the chances of getting 1, 2, 3, or 6 is the same. And with this selecting marbles that we just saw, you see there's equal chance that you pick the first red marble. There's an equal chance that you pick the third green marble. So like the chances of picking any one of them is the same. Okay, it's not like the blue ball is very big such that the blue marble is so big such that you'll be tempted to pick the blue. No, they are all of equal sizes, and you don't even look into the bag before you make the selection. It's totally random. Okay, so when we talk about probability where the outcomes are all equally likely to occur, then we say we are dealing with classical probability. We will see other forms of probability, just that for the purpose of our discussion, that's why I placed this there, to tell you that whatever we've been doing, where we've been seeing equal chances of events occurring, we say they are classical probability. Now let me just give you a simple contradictory statement. Now the weather for tomorrow, or predicting the weather for tomorrow, cannot be under classical probability, because the outcomes are not likely. It depends on so many factors. You can't tell me there's a 50-50 chance each day that it will either rain or there will be sunshine. No, it's not a 50-50 chance. At times it goes as high as 95% to 5%, especially during the dry season or wet season. So predicting weather cannot be under classical probability, because the outcomes are not like equally likely. In any case, one is more likely to happen than the other. Okay, so I just brought this in to make you understand what I mean by classical and the ones that are not classical. So that's the formula. You just have to know the event and know the number of outcomes or elements in that event. So looking at our marble example, if you want the event of selecting a red ball, then we have red 1 or red 2. Okay, we have red 1 or red 2. Now the sample space we listed had 2 red, 3 green, and 1 blue. So the number of elements in E is 2, and number of elements in S, as I just counted, is 6. So if I'm to find the probability of selecting a red marble, it will be number of E, which is 2, over number of S, which is the sample space, which is S, as we discussed earlier. So because all the outcomes are equally likely, we just divide the total number of elements in the event by the total number of sample space. Okay. So I think this tests your understanding. We saw it in the previous slide. Roll a die, find the probability of rolling an odd number. So the event of odd number is 1, 3, and 5. So the number of elements in the event is 3. We divide this 3 by the number of elements in the sample space, which is 1, 2, 3, 4, 5, and 6. So the chances of rolling an odd number is 3 over 6. And it is intuitive because we have 3 odd numbers and we have 3 even numbers. So the chances of rolling an odd number is 3 over 6. But what I just did was showing you how you approach the question in exam. Once again, don't worry, we will have a session where we'll solve questions only, a number of them, so that you become comfortable with probability problems. Okay, so that's briefly what classical probability is. If all outcomes are equally likely. All right, so let's proceed to the next slide. So this is an example asking us about the sum of 7 when two dice are being rolled. Okay, so I think we've seen this example, so I wouldn't spend much time on this. I'll just touch on it light briefly and we move on. So sum of 7, the event is 1 6, gives us a sum of 7, 2 5, 3 4, 4 3, 5 2 and 6 1 as we listed before. Now the number of events here is 6, and the number of outcomes in the sample space, as we saw from that 6 by 6 table, is 36. In that case, the sum of 7 equals 6 over 36, which is 1 out of 6. So kindly try the test you're understanding, which says find the probability that the sum is less than 5. So you'll be seeing, you first state your events, you'll be seeing events like 1 1, because the sum is less than 5. You'll be seeing 1 2, you'll be seeing 1 3, but you can't add 1 4, because the sum of 1 and 4 is 5. It is not less than 5, it is equal to 5, so you don't bring it. You can't add 1 5, you can't add 1 6. Then you come to 2. So you can add 2 1 because the sum is less than 5. 2 2 is also less than 5. You can't add 2 3. So you do all these, you choose the outcomes where the sum is less than 5. That will be your event, your E, set E. So after that, you come to number of E, where you count the outcomes in E. So if E has 7 elements, then the number of E will be equal to 7. Okay, then you divide by the total sample space, which is 36. That's how it is done. So please try your hands on it. Okay, so let's proceed to the next slide. So we have the interpretation of probability. Well, you might not see this in an exam, but it is very key to know, so that it will help you in your day-to-day problem solving and understanding of questions. So probability also represents a long-run relative frequency. So if we say that the probability of an event is 1 over 6, it means that when we conduct, okay, let me give you this simple example. Okay, let's say we toss a coin 10 times, and let's say these are the outcomes. So we have the first one, when we toss, we had a head, a tail, head, tail, head, tail. How many are there? 1 2 3 4 5 6 7 8 9. Let me add another head. Okay, so let's say we tossed we toss the coin 10 times, and these are the outcomes. So when we toss, we put the outcome down. Now, looking at what we have here, how many times did head occur? I think 7 times, and tail occurred 3 times. Well, looking at this data, you can't just conclude that, okay, from what I've seen, it means that when someone tosses a coin, then there's a 70% chance that the person will get a head because of what I'm seeing. Because I tossed the coin 10 times and I had 7 heads. That means tossing a coin, you have 70% chance that you get ahead. No. Why is that wrong? That is wrong because it is not in the long run. You just did 10 tosses. 10 tosses is not sufficient statistically to make a conclusion. So for you to accurately make a conclusion, you need a very large number of sample points. So you have to do the experiment repeatedly, maybe 1,000 times, or 1,000,000 times, or 10,000, or the number of times you should conduct the experiment for you to make a judgment should be very, very high, not just 10 or 50 or 100. Then you say, oh, I had 60 heads when I toss the coin 100 times, so there's a 60% chance that when anybody tosses a coin, they will get a head. No, that is wrong. So studies have shown that, or when you do it yourself, you realize that when you do it for a very long period of time, or when you conduct the experiment continuously, you realize that the number of heads that you are getting is almost the same as the number of tails. That's what happens when you conduct it repeatedly. You end up getting the number of, so let's say you do it for 1,000, or you toss the coin 1,000 times and record the outcome. You see that you might get heads maybe 540, and tails will be 460, or something very close. So you realize that the probability will be almost 0.5. Remember, 540 that you got for heads, when you divide it by 1,000, you are getting 0.54. Let me put this down. So you get heads 540 times, and the total toss is 1,000. So you realize you get 0.54, which is approximately 0.5. Okay. And what do you get for tails? 460 over 1,000, which is 0.46, which is approximately 0.5. So when you increase, so that's the 0.54. So when you do the same for the tails, you get 0.46, which is also approximately 0.5. So what I'm saying is, when you continue to do and do, you realize that the probability will be, both of them will be approaching 0.5. Yes, that's what we term as long run relative frequency. That when you do the experiments continuously, yes, the probability approaches the what you obtain from the classical probability. When I say classical probability, I mean when we toss a coin, by the definition of classical probability, what is the probability of getting a head? So when you toss a coin, the sample space is head and tail. So by classical probability, the event of getting a head is H, and this is 1 out of 2. So I mean, when you do the experiment continuously for a very long time, you realize that the total number of heads that you get, when you divide it by the total number of times you've done the experiment, it will be moving very, very close to 0.5, unless you don't do it for a long time. Okay, so that's what I mean by when it occurs in the long run, the probability approaches what we obtain from the classical probability. Okay, So interpret what a probability of 0.25 means in terms of frequency. Okay, so you can say let's assume we are picking a ball. So there are balls in a confinement, a very large number of them, and we are picking them at random. They are either of color red or black. Now we pick, and we pick a million of balls randomly. Now we realize we had let me say 245 red balls after picking a million of them. So dividing this by, sorry, let's use 1,000 instead. Sorry about that. So 1,000, and we realized we had 245. So in that case, we have 0.245. Now we continue to pick, and now we randomly pick 10,000, and realize that after picking 10,000, we are getting 2,509 red balls. In that case, this probability is also 0.2509. Okay, so what do we see? When we approximate each of them, we are getting 0.25. So we say that when you conduct the experiment for a longer period of time, the probability of getting the red ball is approximately 25%. So we can conclude that the number of red balls in the confinement from which we are picking constitutes 25% of the total red balls. So we can say that for all the balls in there, 25% are red because of this long run experiment that we've conducted. But you can't just do 10 and say that because 8 out of 10 were red balls, then 80% are red. That's very false. You have to do it for a long period of time and look at how the probability is behaving. So you do for 1,000, you do for 10,000, you do for 100,000, you do for 1 million, and you realize that the probability is around a certain value. Yes, that value is the percentage of red balls in the confinement. Okay, sure. So that's the interpretation of probability. It tells us the long run relative frequency. So let's make progress from here. So now we have some properties, or the two main properties of probability. So one is that the probability is strictly between 0 and 1 inclusive. You can never get probability outside this range. So 0 means that the chances, there's no chance at all. Remember, probability deals with chances. So if there's no chance at all, we say 0. We don't give you negative. I don't know what you do to deserve that. But if there's no chance for you at all, so let's say you have red balls, green balls, and blue balls, and you are being asked, what's the probability that you pick a black ball? Remember, there's no black ball. So we say that there's no chance, or the probability is 0. We don't say the probability is -5. No. If there's no chance at all, we say 0. And if there's 100% chance, we say 1. So let's say a bag contains all red balls. What's the probability that you pick red ball? Don't say because it's so likely, so you are saying the probability is 1,000. No, it can't be 1,000. If it is sure, we say 100%. You know, 1 is the same as 100%. Okay, so when the event is a sure event, we say the probability is 1. We don't assign any number beyond 1 or below 0. So you can have values. So when you solve a probability question and the question is asking you to calculate a probability, do well to get values within 0 and 1. So you can get a 0.9, which means 90% chance. You can get 0.3, which means 30% chance in that order. Okay, sure. So you always make sure any probability value you see is between 0 and 1. Now the second one is saying the sum of probability of all outcome in the sample space equals 1. Let me do a very small illustration here. So you're saying that the sum of the probabilities of all outcome is 1. So let's say a sample space of rolling a die, you have 1, 2, 3, 4, 5, and 6. Good. Now, what is the chances of getting 1 or the event of 1? Because 1 appears only once, the chances is 1/6. Chances of getting a 2, let's add it to the 1. So chances of getting 2, because 2 appears only once or appears once, we have 1/6 for 2. So all of them appear once. Okay. Oh, it's more than that. Let me clean. Sure, so the chances of getting a 1 is 1/6 because it appears only 1. When you have to roll a die, the chances of getting 2 is 1/6 because it appears 1. If it happens that 2 appears 3 times, then the chances will be 3 over the total number of elements in the sample space. Okay, but each of them appears once. In that case, obia or each of them has a probability of 1/6 of appearing. Okay. And the second property is saying that when you sum all these probability for each of the outcomes, so 1 has 1/6, 2 has 1/6, 3 has 1/6, each of them has 1/6. So when we sum the probability for all of them, it should be equal to 1. Okay. So let's say in a classroom, 40% are, let me see, males. Okay. Then automatically 60% are females, because we want it to work in such a way that when we sum the probability for all the outcome, because the outcome is either a male or a female, so when we sum the probability for male plus probability of female, because there's no other group left in there, it should give us 1. Okay, but you can't tell me that maybe 40% are of age 20, then 60% should be of age 21. No. Remember, there are other outcomes in there. But when the outcomes are full, or there is no way we can add other outcomes like the male and female, if male is 40, then the female should be 60, because when we sum the two outcomes, it should give us 1. But when someone is age 20, you can't say 21 should be 60%, so that when I sum them, I'll get to 1. Remember, there can be someone with age 23, age 19, and the rest, unless you are strictly told that the people in there are either of age 20 or 21. When you are given this, I mean there's only two outcomes, 20 or 21. So if 20 is 40%, then automatically 21 should be 60%. Aside that, you can't just guess the probability when there is the possibility of other outcomes. Okay, so the second property is saying when you sum all the outcomes, you should get 1. It's a very, very, very important probability and property. Okay, so we will meet that while we make progress. So test your understanding. Which of the following probabilities are valid? So 0 is valid. It means there is no possibility it will never occur, or the number of outcomes in the event that you want is 0. There's nothing in there. There's no way an outcome will be in the event that you want. Let's say you are rolling a die, and the event you want or what you're interested in is getting 8. How would you get 8? So in that case, we say that the number of outcomes that will satisfy your event is 0. There's no outcome that will satisfy your event. In that case, you get 0 over the sample space, which is the same as 0, meaning it's never possible to get 8 when you roll a die. So 0.5 is possible, 50% chance. 1.2 is not possible because it's more than 1. Negative 0.1 is also not possible because there's no probability that it's negative. And 0.5 is also possible. Okay. So explain why outside 0 to 1 are impossible. That's what I explained to you. That for the worst case is 0. And for the best case is 1. You can't go beyond that. Okay. So we move on to the next slide, where we have 3 approaches in assigning probabilities. Okay. So let's discuss them one after the other. So the first approach is the classical approach. The most popular way when we say events are equally likely, but classical probability is mostly used for the basics of probability. But once you move ahead, you will notice that in this world, not all situations are based on equal likelihood of occurrence. So let's say weather, it will either rain or it wouldn't rain. So 50-50, no, it's wrong. Or there's a sport between 2 teams and you say, oh, it's 50-50. No. If a super, or let me say, a very strong team is playing against a very weak team, you can't tell me the probability is 50-50. So in real world, classical probability reduces, though there are still cases where we apply them, but there are a lot of modifications that are being done on them. So classical probability, as we saw, occurs when we assume that all the outcomes are equally likely, like the roll of a die, toss of a coin, selecting a marble. All these are based on the idea that each of them has equal chance of happening. The chance of getting head is the same as chance of getting tail. Chance of selecting first red ball is the same as the chance of selecting first green ball. That's what we call classical probability. Now the second one is called the empirical or the relative frequency. This is what I was explaining when we were talking about long run relative frequency. So let's say in a confinement, you don't know the number of balls in there. You don't know. But you want to look at the behavior of the probabilities and assign the probability of or the percentage of red balls in there. So let's say there's a confinement and you don't know you know that there are red balls in it and you know that there are black balls in it, but you don't know the percentage which are of color red and you don't know the percentage which are of color black. So you want to do some experiments or use past data to see if you can assign probability of red, or you can give the percentage of red balls in the confinement. So this is what you do. You will be drawing them one by one. So maybe the first 100, you look at the number of balls that are of color red. You look at the number of balls that are of color black. Okay, you write the probability down. You keep drawing. So you draw 1,000. Okay, when I drew 1,000 balls, I'm getting 150 to be red and 850 to be black. Okay, let me continue. Then you keep drawing. You draw 10,000 balls. Okay, so you study. So this is what you do. That's what we say is based on observed data. Okay, what you see is what you use to assign the probability. You don't know the number of balls in there, so you have to use what you observe from the experiment you are doing, then you assign the probability. So you do this drawing. So when you draw 100, you write the probability down. When you do 1,000, you write the probability. 10,000, 100,000, 1,000,000. So you do all that, and you realize that the probability of red is around, I guess, maybe 0.149, 0.151, 0.152, 0.15, 0.148. Then that should tell you that the probability might be or can be assumed to be 0.15 or 15%. Now you can make a good judgment that based on my observed data, I can say 15% of the balls in there are red. So that's a way of what? Assigning probability. Okay. And the last one is subjective. So that one is your personal judgment or belief. That's what maybe we see with sports. So maybe this team is playing another team, and looking at, or from your own judgment, okay, so these days this team scores or performs so well. Okay, this team, when they meet this particular team, they perform badly. So you make all those judgments and come with the probability that, looking at things, I think there's a 60% chance that team A would win this match. That's your judgment. That one is not based on equal outcome or based on observed data or whatever. You make your own analysis and give a judgment that this match that you are going to play, there's a 60% chance that they will pass. Or we can even give an example, like, let's say a student going to take a test. It can be subjective. So you say, oh, these days it seems these students, okay, maybe you are the teacher. So, oh, these days this student participates a lot. I can see that now he's getting somehow serious. Okay, now he does his assignments on time. So looking at this, there's a 90% chance that he will pass. This is your judgment. This is personal. Someone might also come and say 80%. You can't say the person is wrong. It's subjective. It depends on the person. Okay. So when we assign probability in this way, we say it is subjective. Though it's the most least used approach compared to the classical and empirical. In fact, when you go to the industry, when you go to the work field, we mostly use empirical, because that one is based on what we see. And because outcomes in the world are not usually equally likely, we don't usually use the classical, although they come up in some situations. But the most used is the empirical. The subjective will work if the person is very experienced in the area he or she is working. That one, he doesn't need so much data. Remember, data are not always right. So a very experienced person can combine factors and give a very good judgment about the probability. So these are the three approaches we'll study now of how we assign probabilities. Alright, so let's proceed. So test your understanding on the previous slide. Identify which approach is used if a sports analyst predicts a team will win based on past matches. This example is trying to be stubborn. It mentions sports analysts predicts, and it also mentions past matches. So what do you think? You can pause the video and tell me your what you think about this. Okay, so in my opinion, the sports analyst is making the prediction based on past matches, observed data. It's not based on his feelings or what he thinks. So in this case, we say this is empirical because he is making the judgment based on past matches. Okay, so it's not from his knowledge, but from what he has witnessed a couple of matches that they've played. Okay, so this will fall under an empirical way of assigning probabilities. So I think we are almost through. Okay, so before we end, we will discuss what we mean by complementary events, which is also a very useful property in probabilities. Complementary events. So an event, if E is an event and the complement is EC, or in other words E prime, then when you sum the probabilities, it is equal to 1. And you should be very careful about this. So for instance, if you take my example about the age of students, where I said one of them is of age 20, you can't say 21 will be a complement to 20 because there might be other ages. So complement only comes in when there are two possible outcomes, a male or a female. So the probability of male will be the E, and its complement will be the probability of female. Or if in a test 60% of the answers are true, then we know that true goes with false. There's no other outcomes we can add to this. So in that case, false will be a complement to true. So if the probability of false is 60, then if the probability of false is 60%, then we know that the complement of false will be 40%. And in real life, the complement of false is true. Okay. So they should always sum to 1. You will see this a lot in our calculations. We will use this relation a lot. Okay. So when we have probability of getting an even number to be, say, 30%, then the complement of even number, which is odd number, will be 70%. So if in a set 30% are even, then automatically you can deduce that 70% will be odd. So that's what we mean by complement. When there are two outcomes and you know the probability for one, no one will even tell you to deduce the probability for the other. And remember, it's not necessarily male or female, true or false. It could be that like what we see here, not rolling a 3. So if the probability of 3 is 40%, then the probability of not rolling a 3 is 60%. If the probability of attending a class is 35%, then the probability of not attending the class is 1 minus 35%, which is 65%. If the probability of winning a match is 80%, then the complement not winning a match is 20%. That's how simple complementary events are. So always correctly determine the complement of the original event. If you're able to do that, then you can calculate 1 minus the original event to get the complement. We will use this a lot, so make sure you understand it clearly. Okay, so let's move on to the last slide of it's the same exam type questions. So let's discuss it quickly and move on to the next lecture after this. So 2 dice are rolled. Write the sample space. This is what we saw, the 6x6 table. So you list 1, 2, 3, 4, 5, 6 here. Then you list 1, 2, 3, 4, 5, 6 also here. So this is the outcomes for the first or the second row, any of them. And this is the outcome for the other row. Okay, so you do that, this becomes 1, 1, 1, 2, 1, 3 in that order. That's the sample space. B is find the probability that the sum is even. So you write the event E, then you list all outcomes that makes the sum even. We have 1, 1, we have 1, 3, we have 1, 5, we have 2, 2, we have 2, 4 in that order. Okay, so you list all of them, then you count them. If they are 15, then you divide it by 36. That's the number of sample space in order to find a probability that it is even. So try all these based on what we've discussed. C is find the probability that the sum is 7, of which has already been discussed. I remember getting 6 over 36, which was equal to 1 over 6. Now, a card is drawn from a standard deck. So a standard deck card, like the playing cards, it has 52 cards in it. Keep this in mind. You might not be told in an exam. So a standard deck or a deck of cards has 52 cards in it. Okay. So find the probability that the card is a face card. When we say a face card, cards that have you see these faces on them, maybe kill, the queen, the jack, and the king. Okay, so we have 4 queens, 4 kings, and 4 jacks, which gives a total of 12. The number of events is 12. You divide by the sample space, which is 52, and that's how easily you determine the probability. Okay, 4 queens, 4 kings, and 4 jacks, giving us a total of 12. So 12 divided by the entire deck, which is 52, will give us the probability of getting a face, because we know that each face or each card is equally likely to occur. So we use classical probability for this. The chances of getting killed is the same chance of getting 7. Because there are 52 there and you are picking one. You can pick A, you can pick J, you can pick 10 or other thing. So they have equal chances. So you use the classical approach to do that. Find the number of events of face card divided by the sample space. So find the probability that the card is not a spade. And one wise way to do this is to find the probability of getting a spade. When you are done, then you find the complement of a spade. Okay, so let me solve it for you. So the probability of a spade. Remember, there are 52 cards, 13 hearts, 13 diamonds, 13 club, and 13 spades. Or just divide 52 by 4. Because you know there are 4 different type of cards. We have the spade, hearts, diamonds, and the club. So that's how we determine that there are 13 spades in the deck. So the probability of getting a spade is 13 over 52. Then the probability of not getting a spade, so we either write it PC or PS prime or PS bar. The prime is, okay, let me write the prime here. PS prime, like this. So all these denotes the complementary probability. PS prime or PSC or PS bar. They are all ways to write complementary probability. So we determine the probability of getting a spade to be 13 over 52. So the probability of not getting a spade, remember, a spade plus not a spade is 1. So we now want not a spade, which is 1 minus what? Spade. And we determine probability of getting a spade because there are 13 spades. We have 13 over 52. And when you punch it, the answer that you get is the probability of not getting a spade. So this is an application of the complementary. Okay, the question gave you not a spade, so you can find for a spade because it's easy to know the number of spades, which is 13. Because if there are 52 and there are 4 times, then each of them has 13 number of cards. So probability of spade is 13 over 52. So not a spade will be 1 minus probability of spade. I learned this so well because you will definitely apply complementary probability here. So we have the last one. A bag contains 2 red, 3 green, and 1 blue marble, just as we saw. 1 marble is selected. Find the probability of selecting a red. So the event of red is either R1 or R2. And the sample space is R1, R2, Gen 1, Gen 2, Gen 3, and a blue. So the number of events is 2. We just have 2 outcomes here, 1, 2. And the number of sample space is 6. We have 6 in total. In that case, the probability of selecting red is 2 over 6. Okay, is 2 over 6. Remember, probability is equal to number of events over number of sample space. Good. So the last one, probability of not selecting blue. We can find what's selecting blue, then we find the complement. So probability of selecting blue, because the number of events of blue is 1. Blue has just one outcome. And the number of sample space is 6. So the probability of selecting blue is 1/6. So the probability of not selecting blue is 1 minus selecting blue, which is 5/6. Okay, so that's also another application of complementary events. So if you see not selecting and you feel it's easy to find the selecting, you can find the selecting, then apply the selecting to find the not selecting. And remember, not selecting is always equal to 1 minus selecting. Okay, so that brings us to the end. Let's have a quick summary and we meet again in the next lecture. So we've seen what random experiment and sample spaces are. We've seen how to represent sample space using tables. We've understood what simple and compound events are. We've seen the classical probability approach formula, and we've solved exam type probability questions, or let me say discussed, because it wasn't a rigorous problem solving. Those sections will also come. And we've also practiced questions after each slide to strengthen understanding. You know, it is key to learn and practice at the same time. You can study, and without practice, you'll be found wanting when it's time to produce what you've learned. So I'll always make sure for each slide you have some questions to discuss to strengthen your understanding. Once again, my name is Nasiruddin, a tutor for Actuarial Science and Statistics on the Inorganic Tutors Institute. I'll see you in the next lecture when we discuss students' concepts of probability and how to apply them in exam and